Hello friends, welcome to Risingpearl.com. This is series 13 where we're learning a great deal on surface areas and volumes. This is webisode number 12 and we are going to continue to find out how to solve questions on surface areas of complex shapes, that is shapes that are made up of a combination of simple solids. This is part 3. In the last two episodes, which was episode 10 and 11, we started to look at how do we solve such questions. Now one of the things that I have been trying to repeat over and over again on purpose is to make sure that I highlight you the three simple steps that you keep in mind when you answer these type of questions. So what are they? The first is that try and visualize in your mind which simple solids make up the given complex figure. So you will be given a toy or some sort of an object and you want to break it down into simple components. By that I mean whether we are adding one cube on top, a cuboid on top of a cube, or if we are taking a combination of a cube and a cylinder, or one cube, multiple cylinders, cones, spheres, etc. That is, we try and visualize the given complex figure is made up of what all simple solids. And by simple solids we are referring to cuboids, cubes, cylinders, cones, spheres and hemispheres. So after we finish doing that, then we want to find out that which areas we need to add and which areas we need to subtract to get to our required area. So now this is very important, this step too, because like we have seen in the last two episodes that if we are talking about surface area, most of the time the surface area which is inside of a solid, that is not normally used. Depending on what the question is, again very hard to generalize it, but when you combine solids, when you combine them, some areas they disappear, they basically go inside one another. And these steps we are going to continue to see over and over again as we answer these questions. And finally, the third and final step is that after we know which areas we have to add, subtract, then the actual computing of those areas and then calculating the required area using step 2, right? So these are three simple steps that we will basically use almost always when we solve these type of questions. Now let's take a look at one question. A cubical block of side 14 centimeter is surmounted by a hemisphere. So we have a cubical block on the bottom and we have a hemisphere on the top. The measure of the cubical block is given to us. When a cube has all three dimensions the same, that is the length, breadth and height are all same for a cube and they are all 14 centimeter in this example. What is the greatest diameter of the hemisphere can have? The hemisphere, the only one measure that we need for a hemisphere is the radius. The radius is not given, but the question is asking us what is the greatest diameter the hemisphere can have? That is the first question. It's a two-part question, and the second part is find the surface area of the solid. So first let's try and see how the solid may look like, the final solid. So we start out with a cube and we have a hemisphere. Now the hemisphere sits on top of the cubical block, so something like this. But if you really think about it, there are three different scenarios and they are all highlighted here. So one is that, in each of these cases the base is the cubical block, right? And for the base each side is 14 centimeters. So this is 14, this is 14, this is 14, and this is true for all of them. So again it's the same over here, right? Now but if you look at the hemisphere, so in this case we have taken such a hemisphere. If I think this is the radius r, the hemisphere is actually spilling out of the cube. If you notice it, see this is the edge of the cube. If I were to just highlight it like this, this is the edge of the cube and the hemisphere actually is spilling out of the cube because the size, the r is so big that it is coming out of the cube. In this case the hemisphere is just sitting exactly on top of the cube, and here the hemisphere has a radius which is much smaller, so the hemisphere is well within the cube. Obviously in each of these three examples the hemisphere is sitting on top of the cube, so we are talking about the hemisphere and the top surface, right? So here hemisphere is coming out of the top surface of the cube. Here the hemisphere and the cube, they exactly line up, and here the hemisphere is much smaller than the cube. So our question is, what is the greatest diameter that the hemisphere can have? So now let's focus on this particular scenario. So if you think about it, so I have on purpose basically faded these other two drawings. So here, if you look at, this is the top view. This is the top view. Top view. So if you were to see it from the top, how will it look like? So this is the top surface of the cube. And now our hemisphere is going to sit something like this, right? So in this particular case, what happens is that this radius r is such a radius that is, so if I were to think the center is this, so this radius r exactly lines up with the top surface of the cube. In other words, this length, that is r plus r, this length r plus r is exactly equal to the length of the cube. So r plus r is exactly equal to 14, and r plus r is nothing but 2r is equal to 14, and 2r means the diameter. So diameter is equal to 14 centimeter. So in other words, what happens is that if we take the diameter equals 14, keep in mind this is the top view, and the one which is the circle is the view of the hemisphere from the top, right? And I have highlighted it in dark blue. So if the diameter of the circle, the hemisphere, is exactly 14, then it fits the cube. If we go with the diameter which is greater than 14, then the sphere actually comes out of the cube, like the way we had it here. So the cube actually was coming outside, the hemisphere was coming outside of the cube, right? And if we take the diameter less than 14, then the hemisphere basically was well inside the cube. So if we were to find out the maximum or the greatest diameter that fits, then the hemisphere needs to have a diameter of exactly equal to 14. Then the hemisphere will exactly sit on top of the cubical block. So it's important, friends, to take a moment and visualize these questions, right? So if you are not able to follow any of the steps that we talked about, so please pause the video and go back and play that again to make sure that you are able to exactly follow the way we are discussing it over here. Now let's clean this up, and now we have answered the first part of the question, which is what is the greatest diameter the hemisphere can have, and answer is that is equal to 14. Now what about the second part, which is find the surface area of the solid? Now the surface area of the solid is, let's try to break it down. First is the curved surface area of the hemisphere. Clearly we can see it. So this is the curved surface of the hemisphere. Remember, whenever we talk about surface area, think about, we want to paint that surface, right? So we want to paint it. So what is the area on which we are going to apply our paint? So the surface area of the solid is the curved surface of the hemisphere. So obviously this entire curved surface of the hemisphere that is there, right? Then plus the surface areas of 5 faces of the cube. Why are we talking about 5 faces? Well, we know a cube has 6 sides, right? So we are talking about this, the front, right? We are talking about the back, which is over there, front, back, the left side, the right side, and the bottom. So 5 sides, by that 5 faces of the cube, We are talking about front, back, 1 and 2, left, right, 3 and 4, and the base, which is 5th. What we have not talked about is the top. And this is a top view. So because this is a top view, we can actually look at it clearly as to what is going on the top. This is a top view. So the total surface area of the cube is, of the solid, is curved surface area of the hemisphere, number 1, which is this one over here, right, which is, let's shade this, this is the curved surface area of the hemisphere, plus the surface areas of 5 of the 6 faces of the cube. The only face which is not factored in is the top, and we are going to come to that here. And then plus the surface area of the top face of the cube, which is the 6th face, but minus the area of the circle, which is the base circle of the hemisphere. Because now if you think about it from the top, now this is the entire surface area, which is kind of in the light blue. That is the entire surface area of the top of the cube. But we have the hemisphere sitting like this, right? It means the only part which will be seen will be this part, which I am highlighting right now, right? Because the part which is highlighted in dark blue is actually going to be covered by the hemisphere, or the base of the hemisphere. So as far as the top face is concerned, the area for the, remember, like we talked about in this, so the surface area has 3 parts. 1 is the curved surface area of the hemisphere. 2, 5 faces of the cube, front, back, left, right, and the bottom. And this is the third one, where we are breaking it down, which is the top face of the cube, but it will be the top face of the cube minus the area of the circle, which is the base of the hemisphere. So that will give us the total surface area of the solid. And this is what I have been talking about when I mentioned that we want to continuously go back and look at these 3 steps. Step 1, step 2, step 3, right? So the step 1 is telling us that we have a cube in this particular case, and we have a hemisphere. So sphere, we have a hemisphere, right? And then this second step, which is so important, where we are trying to find out which areas to be added and which to be subtracted. So we realized here in this particular case that we would need to add the area, the total surface area, the curved surface area of the hemisphere, plus the 5 faces areas of the cube, plus for the top face we have to take the top surface area, but we have to subtract the area of the circular base, because that circular base is the base of the hemisphere. So if I were to take the paint analogy, if I want to paint this entire block or the entire solid some other color, then the base of the circle is actually inside the solid and I cannot apply paint on it, right? So I have to subtract that area out. That area actually disappears. So that is why it is important to go back to these 3 steps whenever you have these kinds of questions. Now let's continue with our question. Now that we understand it, now we have to actually write the formulas, and the third and final step, find each of these individual areas. So we have 1, we have 2, and we have 3. So we have to compute each one of them and then add them to get the final answer, right? So the curved surface area of the hemisphere, the formula for that is 2 pi r square. And what is r? Well, we know that r is equal to 7, right? So this will be 2 pi times 7 square, or 7 sevens are 49, and 49 times 2, that will be 98. So this will be 98 pi, this much centimeter square. So the curved surface of the hemisphere is 98 pi. What about the surface area of the 5 faces of the cube? We know that a cube, if this side is A, this side is A, and the height is A. So each of the face is A square, A times A, right, or A times A. So for 5 faces, it will be equal to 5 times A square, where A is 14 square. So you can find out what this value is, that much centimeter square. Now the surface area of the top of the cube, right? So the surface area of the top face of the cube will be, so that minus the area of the circle. So that will be actually equal to, so base of the hemisphere, right? So this one will be equal to, so it will be 14 times 14, 14 square, that is the area of the square at the top, minus, so this is the surface area of the top face of the cube, minus pi r square. R is 7, r square. So this will give us the third component. So the final answer will be, we have to simply add 98 pi, and you are going to replace the pi with 22 by 7 and calculate what value you get. So this plus this, right, plus whatever you get here from 14 times 14 minus 49 pi. So if you add 1, 2 and 3, you will get the required answer, which is the total surface area of the solid. So friends, I wanted to make sure that you take the time to understand how you need to think when you answer these kinds of questions, and what is the step by step way of solving these questions. You are always looking for the area that disappears, the area that you cannot apply the paint on. So when we talk about combination of solids and surface areas of combination of solids.